and accept that.
Okay.
So I would like to invite Albert Much, a very young and dynamic researcher who has published in journals that are personal and very jealous, Classical and Quantum Gravity, Journal of Mathematical Physics is his cup of tea, actually, and his research interests lie in non-commutative geometry and quantum field theory in curved space-times. He has completed his studies in Vienna and in Leipzig. He has Syrian origins, and he speaks many languages. Arabic.
No, I was just born in Syria.
Ah, you were born in Syria.
I have Iraqi and Palestinian origins.
Ah, amazing blend.
So,
but you were raised in Vienna, so you are Viennese,
right?
In the passport. So
yes,
yes.
First and foremost.
Exactly. So nice to see you, Albert, and we're looking forward for your talk.
Okay, thank you very much, Kyriakos, for this very nice invitation. So yeah, the title of my talk is Non-Commutative Quantum Field Theory, and the question if this is a viable approach to quantum gravity. So the main motivation, so to speak, for this talk is the question: does non-commutative geometry award us with a theory of quantum gravity? Because this is basically what is the selling point of studying non-commutative geometry, and this is basically the reason why physicists also got interested in that. And there is also a sort of physical motivation for non-commutative for regarding things as non-commutative geometry in physics. It is a very old argument that goes back to Rieffel, basically, that if you try to localize a space-time point with arbitrary accuracy, you will start creating black holes, basically. So you put so much energy in such a small region that the gravitational collapse will cause this region to become a black hole. So basically, the space-time points are physically not well defined, and this was also something that was known to Riemann, actually. Also, he said his geometry is very nice and so on, but it has to be modified on very small length scales, and I think that is quite an ingenious remark. And so the way we do quantum field theory in curved spacetimes is we sort of neglect certain aspects of quantum gravity. So basically, we take a classical spacetime and we study quantum fields on that classical curved spacetime. Yeah. So in the approach that has given us a lot of a lot of physical knowledge and insights. You take the spacetime as a classical entity, as a manifold, differentiable, smooth, and everything, and you define your quantum field theory on that spacetime, and then you calculate whatever you're interested in, right? And that has applications to cosmology, to black hole thermodynamics, to even the question if particles themselves are a well-defined concept on their own. And so one can consider quantum field theory in curved spacetime as a zero-order approximation to quantum gravity, okay? Because it's basically it is as if you neglect the quantum nature of spacetime, whatever that may be. And in non-commutative quantum field theory, what you do is you take a quantum field theory and you define it on a non-commutative spacetime, whatever that is. That is depending on who you talk to. Everyone has their own interpretation, but the way I think one has to see it is we have, it's like in quantum mechanics. In quantum mechanics and in mechanics. In mechanics, you have classical mechanics, you have symplectic geometry, you have the phase space, X and P, so your coordinate and momenta, they all are given by points, and it's a classical manifold, basically, symplectic manifold. When you go to quantum mechanics, what happens is that you start quantizing that phase space, basically, right? So you place your your space-time points and your space point and your momenta points by operators. And this is exactly what is done in non-commutative quantum field theory, sort of. So my idea is, let us fuse those two. Let me fuse non-commutative geometry or non-commutative quantum field theory with quantum field theory in curved spacetimes to obtain at least, since I'm not that young anymore and maybe not that optimistic. I'm still optimistic, but I'm a bit more cautiously optimistic. It should be at least a first order approximation to a theory of quantum gravity, because you take the quantum aspect of space-time into account. Okay, so that was I hope not a too long introduction. And I mean, my talk is very short actually, so this gives me a little bit of freedom to talk here and there. And so my PhD advisor told me to always have 3 questions in mind when you give a talk. So you have to tell the audience what you're doing and why you're doing it, and then how you're doing it. These questions have to be very, and this is how I like to structure my talk. So what do we want to do? We want to generalize non-commutative quantum field theory in Minkowski space, that is a sort of well-defined concept, to curved spacetimes rigorously. And so I mean, as that would be already so to speak an achievement. But as a physicist, we also want this to make sense not only mathematically but physically. So the end result, the end product that I get, should make physical sense. And the physical sense or the physical sensibility comes into mathematics when we apply principles. Basically, every major theory in physics is built on principles, and the principle in gravity is the equivalence principle. This is the Einsteinian principle. People always draw these pictures with elevators, and basically the equivalence principle tells you that locally everything looks like Minkowski, everything looks flat. Okay. And this is a huge principle that leads to general relativity and all its achievements, right? So I want to prove that whatever my end result is, it should comply with the equivalence principle. Otherwise, we can just disregard this or discard this. So why do I want to do this? Well, first of all, I want a theoretical proof at least, that non-commutative spacetimes, or quantum spacetimes as I like to call them, have a physical validity. And furthermore, I want to prove that they are connected to quantum gravity. So it's a twofold motivation, so to speak. Now, okay, before we get into the business of how to fuse those two, let me explain first a little bit the individual parts. So quantum field theory in curved spacetimes, I will give you a short and most probably imprecise overview. So you can construct quantum field theories rigorously on globally hyperbolic spacetimes, or in globally hyperbolic spacetimes. These, I mean, Kyriakos is an expert on those spacetimes, of course. And the major advantage from a physicist point of view of these spacetimes is you have a well-defined Cauchy problem, basically, because I mean we want to solve some differential equation at the end of the day. And of course, I mean, the advantage is also there exists a direction of time, right? You can choose your time direction. But the disadvantages from the perspective of quantum field theory is that there are no preferred states. Now, in Minkowski space, which is the flat Lorentzian space, some physicists call this Minkowski space, mathematicians call it flat Lorentzian manifolds. The quantum field theory supplies you with a preferred state because the vacuum vector, so the vector where nothing happens, is invariant under the symmetry group of Minkowski. However, in globally hyperbolic spacetimes, you can have a globally hyperbolic spacetime that has no symmetry at all. So you cannot sort of choose a preferred vacuum state. And the problem, I wouldn't say it's solved, but it is well, you will see. I mean, it is dealt with or handled with by the so-called GNS construction. So, I mean, since most of you are mathematicians, you probably know this. For a given state, so a positive linear functional, omega over a unital star algebra A, one obtains a quadruple. So give me a state, a positive linear functional, and a star algebra, and the GNS construction supplies you with a quadruple, which is, I mean, usually sometimes a triple. So if it's a C-star algebra, it's a triple, and if it's a star algebra, it's a quadruple, which is made out, which basically gives you the Hilbert space, a dense domain of that Hilbert space on which your algebra is defined, a representation of your operators, and a vector psi omega that is basically something like the vacuum. So the field operators are then given, sorry, this should be the same F. I'm sorry for this. So so these are elements of your star algebra. You smear them with some functions, and the point is the GNS construction gives you a representation of that, because what is the saying? No quantization without representation. Okay, and this holds here as well, because I mean, if you work just with a star algebra, this is some abstract concept that with which you cannot measure anything, right? If you want to measure something, you need to project this somehow to a Hilbert space where you have a scalar product, you have a expectation value, and all this nice stuff. So the endpoint function is given then by, so you take products of these elements of the star algebra, and this is given by the expectation value with regards to this vector psi omega of p omega phi of f1 to p omega phi of fn. So it's just the product, okay? And these are the fundamental objects in quantum field theory. And of course, if you have a quantum field theory that is, if you have a quantum field theory that is, or if you have a state that is quasi-free, this means you can express all the endpoint functions just by the two-point function, and this will become important in a while. So then all endpoint functions are just basically sums and products over two-point functions. So basically, the two-point function is the central element then for these theories. Now you see here, I just said give me a state, but what kind of state? And there's a huge debate going on, and not only debate, but I would say a huge research that has been done on what the best states are to use, and the best states so far that we can think of are the so-called Hadamard states. Because they resemble the singularity structure of Minkowski. Okay. So basically, a Hadamard state is defined such that in the convex neighborhood C of Mg's of the manifold or Lorentzian manifold M and metric G, the Hadamard parametrics is given by this function plus some C infinity. But this is not really what is important. So you have U and V, these are some C infinity functions. And then you have a term that goes like 1 over sigma square, which is basically made out of the geodesic distance function plus the difference between the local time coordinates that increase towards the future, and the logarithmic term of this sigma square epsilon. Here you have a lambda square due to a length scale, right? Because I mean, okay, this is something that physicists always take as so to speak the probe, because in the end this expression gives you a length square, so you have to divide it by a length square so that you can take the logarithm of something that is dimensionless. Okay, this is how the Hadamard parametrics look like, and then that means that if we have states of that way, they resemble the singularity structure of Minkowski. So if you take the Minkowski quantum field theory, you calculate a two-point function. Basically, you have a square, a quadratic divergence plus a logarithmic one. Okay, and so these are the preferred states. There's many more reasons that I don't want to go into why these states are also very important. So this is a quick overview of quantum field theory in curved spacetime. You take, so to speak, a Klein-Gordon equation on this curved spacetime with some curvature and some mass. This is your star algebra. It's made out of all these phi's that satisfy this Klein-Gordon equation. And then you take as a state a Hadamard state. And with that, you can do the GNS construction to obtain Hilbert space and so on and so forth. Now, so this is the quantum field theory in curved spacetime. Now let me switch to, so to speak, the quantum field theory in Minkowski spacetime. Basically there, you take a quantum field theory on Minkowski spacetime and you deform the product of the fields. So instead of phi of f1 times phi of f2, you have phi of f1 star phi of f2. And this star is given by the so-called Rieffel product. So I don't know how familiar you guys are with the Rieffel product, but Mark Rieffel is a distinguished professor at some very in Berkeley, I think, I mean, one of the greatest mathematicians of our times, I think, and basically the Rieffel product is an associative product. So if you take f star g star h, it doesn't matter where you put the brackets, right? And it is well defined as an oscillatory integral. Okay. And basically quantum field theory, non-commutative quantum field theory in Minkowski spacetime is just, as I said, taking the fields, taking the quantum field theory and replacing the product by the star product. This is what happens. Now, as you see here, what is the star product? So you have the star product of f and g of z, and basically what you do is you translate f by theta x, you translate g by y, and then you multiply this by e to the minus xy, and this is, so to speak, this product. The point is for theta, so theta is a skew symmetric matrix, and if this goes to 0, you see this term cancels, and then you're basically left with a delta function. And then the product goes, I mean, then you have just f of z, g of z plus y, delta of y, and then this goes over into the usual product, okay? And now I want to use this, or to apply this to curved spacetimes. Now the first problem, of course, there are no translations in curved spacetime. I mean, that is what basically curvature is about. So there are no commuting translations that would lead to an associative product. So the point is that the reason that this is an associative product is actually because the translations in Minkowski spacetime, they commute. Okay, this doesn't work, of course, in curved spacetimes. And then the idea given by my dear colleague Markus Fröb was so we worked on this for a few months, tried to. So actually, I told him about this product, and he said, "Well, this isn't Minkowski-nized, but if you go to curved spacetimes, this doesn't make any sense at all." And this initiated sort of this program, and then I told him, "Well, how could we do this?" And then we tried for the Rindler spacetime, which is a very easy spacetime, so to speak. And then because he's an expert on de Sitter, he said, "Well, let us do this on the de Sitter spacetime." And then we tried a few calculations and to do it with the exponential function and so on, and this didn't work. And then Markus came up with the idea: let us embed this spacetime into a higher dimensional flat Minkowski spacetime where translations exist, which is a very good idea. And then we did this, and it was published in Journal of Mathematical Physics. And so we deformed the quantum field theory in de Sitter spacetime, and actually it has even applications to inflationary cosmology. So we looked at what happens, so to speak, because the Big Bang and all these, cosmology models, this is where we think that non-commutativity will have its leading orders. And actually what we found out is that the 2-point function, basically, for such a model has a non-commutative correction to it, but it is exponentially decreasing. Okay, so that means that in the beginning this thing is very important, and the more the time goes on, so it's exponentially decreasing in time, the less the non-commutativity becomes apparent. And this basically is something that we agree upon in cosmology, I think, because there is no traces up to now of some non-commutative structure of space-time. And I generalized this idea to all globally hyperbolic spacetimes in the paper I called Make Deformation Quantization Physical Again, which was a huge mistake to call it that way, but I thought it was funny at the time, but well, okay, you will even learn. And the way to do this and to extend, the idea of de Sitter to all globally hyperbolic spacetimes is by using this theorem by Miguel Sanchez and Olaf Müller, or the idea, theorem actually, that they gave in 2011, which is basically let NG be a globally hyperbolic manifold, then it admits an isometric embedding into the flat Lorentzian manifold for some higher dimension n, okay? This is, this is immensely important. So that means for every globally hyperbolic manifold can be embedded into a higher dimensional flat Minkowski space, which is basically the same idea of Nash, right? For Riemannian manifolds, there's the Nash embedding theorem, but for Lorentzian manifolds, which, as you surely know, is quite more involved. Okay, this basically means there exists, some map from M to Ln with local coordinates xa such that these differential equations have some solutions. Of course, they put on n2 minus 4 constraints on the coordinates because you have in 4 dimensions at least you have your 4-dimensional globally hyperbolic spacetime. You embed that into Minkowski space, into high-dimensional Minkowski space. 4 dimensions are still free. The others are somehow constrained, right? It's like with the sphere, basically. I like to think of the sphere a lot because the sphere you have it S2 is, you can embed this or describe this into R3, and there you have the constraint that x squared plus y squared plus z squared has to be R squared. So you have two directions that are free and one that is constrained. And due to the inverse function theorem, you can also invert that expression, okay? So now we started with the small coordinates of the globally hyperbolic manifold. We embedded it into the higher dimensional one. So we use the big coordinates, and now we can reverse that. But on these big x's, you have translations defined because they are defined on the Minkowski space. That is, so to speak, the gist here. And then I defined a curved star product. So we using the embedding coordinates, we can define an associative star product by basically where z is now the embedding point, and you can define this star product by using these translations. As I said, it's basically the same formula, but now I'm working in the embedding space. Now, if I pull this back, I get a formula of this type, which is basically, which gives me some non-commutative matrix that depends on the coordinates as well. Okay, so now we generalize this Rieffel product to curved spacetimes, and now we apply this to quantum field theory in globally hyperbolic spacetimes. So for a star algebra defined on globally hyperbolic spacetime, Mg generated by Klein-Gordon fields, we have the following deformed two-point function. Basically, as I told you, what this deformation is basically taking the vacuum expectation value or the expectation value with respect to psi omega on phi, so between phi of x1 and phi of x2. Right, so you need to put a cutoff function because these are operator value distributions and so on. This is a bit, some analysis is required here. And then we have a deformed smear two-point function because, these operators are not these are operator value distributions. In order to make them well-defined, you smear with some test functions over that. Okay, this is like some mathematical details. But in the end, we have now a deformed 2-point function, okay? That differs from the undeformed one exactly by this Rieffel product. Now the question is, does the deformation make sense? This is the main, as I told you, the goal is quite ambitious, and the skills are not that high, but the question is still, can we make some physical sense out of this deformation? And for that, there's actually a good answer. So okay, let me define the wavefront set first. So if U is an element of this space of distributions, a pair xk in Rn is called a regular direction for U if there exists some constant Cn such that this holds. Okay, this you probably know from Fourier analysis, right? If you have a so let's say you have a function that is C0 infinity, you know its Fourier transformation is an entire analytic function that is bounded by this inequality. And the definition of the wavefront set is basically the wavefront set of U is defined to be exactly those directions that are not regular for U. Okay, so basically the wavefront set tells you where your function is singular and in which directions also it is singular. Now, why is this useful? First, a few properties of the wavefront set. So as I told you, if you have C0 infinity, you see everything is a regular direction for that function. So the wavefront set is empty. Also, the wavefront set has some nice additivity structure. And if P is an any differential operator with smooth coefficients, then the wavefront set of PU is a subset of the wavefront set of U. Now we define the bundle of non-zero null covectors on the manifold. Basically, you take xi to be an element of the cotangent space of M, where xi is a non-zero null at some point P, and n plus and n minus define U1 that is future directed and past directed. I will tell you why this is important in a second. We say a state obeys the micro-local spectrum condition if the wavefront set of this 2-point function is a subset of n plus times n minus. Okay, why is that important? What does this have to do with physics? If a 2-point function obeys this basically means you have a frequency splitting, once into the negative frequency and one into the positive frequency. And this is exactly what happens in Minkowski spacetime. So if you have a quantum field, you take the 2-point function, you have, so to speak, a positive direction and a negative positive frequency and negative frequency. Okay. Now it was shown by this is a great achievement. Even in mathematics, I think this would be considered a great achievement by Minkowski. He proved that the micro-local spectrum condition is equivalent to the Hadamard condition. So if your 2-point function, if this state is a Hadamard state, then it also satisfies the micro-local spectrum condition. Another important corollary, actually, of this is that if you have two states and both obey the micro-local condition, the difference can only be a C infinity function. This, in a sense, determines an equivalence of classes of states under the equality of some 2-point functions modulo C infinity. Because, I mean, the Hadamard states, these 2-point functions or these states are not unique. You can choose. This is what I meant with the problem was not directly solved, but somehow, well, I don't want to say sugar-coated, but somehow better defined. And okay, so that basically means you have a quantum field theory in curved spacetime, on global hyperbolic spacetime. If you can prove that the wavefront set of the 2-point function obeys this micro-local condition, then you know it is Hadamard. Then you know that the equivalence principle holds, because all the Minkowski spacetime 2-point function satisfies this condition. Okay, so again, you have a 2-point function if the 2-point function obeys the microlocal spectrum condition, so that means that its wavefront set is included in this n plus cos n minus, you know that it is equivalent to the Hadamard, and Hadamard is basically equivalent to the Minkowski, or not equivalent, but is similar to the Minkowski, which means that, again, the equivalence principle. Locally, no matter how curved the global hyperbolic spacetime is, I can choose a coordinate system where or locally I can this thing looks like Minkowski, basically, right? Okay. Now we have a deformed 2-point function. So for the deformation, or for this non-commutative quantum field theory to make sense, we want, as I said, I want the equivalence principle to be satisfied. And it turns out that the state omega, so if you have a state omega that obeys the microlocal spectrum condition, and I deform that state, it will also obey the microlocal spectrum condition. And the proof is a two-liner. Because basically the 2-point function, the deformed one, is equal to a differential operator times the original 2-point function. And as I showed you here, if P is any differential operator with smooth coefficients, then the wavefront set of PU is included in the wavefront set of U. So the wavefront set of the deformed 2-point function is equal to the wavefront set of P omega 2, and this is included by the properties of the wavefront set in the wavefront set of the undeformed 2-point function, which satisfies the Hadamard condition or the microlocal spectrum condition. That means our deformations make physical sense in the sense that I defined what physical sense means. Okay, I mean, this is still like the step 0 in a sense. Okay, we're still at the beginning of this. Furthermore, the deformed 2-point function, of course, is Hadamard, because if the wavefront set satisfies the microlocal spectrum condition, we know by Radzikovsky that it is Hadamard. So that means the deformations are physically meaningful since they satisfy the equivalence principle. Now, I'm sure a lot of you will be, because you're all, topologists and so on, and then you will think to yourself, well, you chose an embedding, and according to that embedding, everything makes sense. What if I choose another embedding? Because, I mean, there's no uniqueness of those embeddings. And basically, if I let IMG and I prime MG be two different smooth isomorphic embeddings, then the corresponding deformed 2-point functions have the same wavefront set, actually. So it doesn't matter which embedding I choose, they still satisfy the equivalence principle. And this is due to the smoothness of the embedding and the deformed 2-point functions. They both obey the microlocal spectrum condition. Because I mean, I didn't choose any particular one. I just, this is very general. So omega and omega prime satisfy the microlocal condition. And according to theorem 7, that means that their difference can only be a C infinity function. Now, if their difference is a C infinity function, by property 1 of the wavefront set, we know that, so to speak, wavefront set of omega 2 theta minus omega 2 prime theta is equal to 0, which means, and since this is the wavefront set is linear, right? So wavefront set of alpha and so on. So I mean, this is the property 1, right? Sorry. So because of this, of property 2, sorry, this is a property 2, we know that they have the same wavefront set. So again, that means it is independent of embeddings. The equivalence principle holds. Okay, basically, I think I finished my talk. So let me conclude and give you a short outlook. So what I was able to show and hopefully convince you is that quantum field theory in non-commutative or quantized or quantum curved spacetimes agrees with the equivalence principle, at least according to the way we did it. The deformation can also be extended to endpoint functions. This is a bit of a technical step. And now we have step 0. If we have step 0 now, the step 1 is, let us apply this to different things, and this is exactly what we are in the process of. So some of my master students, the rigorous framework to examine achievements in curved spacetimes with non-commutative component. So now we have all the achievements of quantum field theory in curved spacetimes, and now we have, so to speak, a generalization of that. And now we want to see what do these achievements give us? So the Hawking effect, quantum energy inequalities, entropy, semi-classical effects, inflationary cosmology, and all that. Okay, and this should lead to a prediction of testable quantum gravitational effects. Okay, because only then a theory can be really considered a true candidate for a theory, for a complete theory of quantum gravity. Yeah, thank you very much for your attention.
Thank you very much, Albert, for this inspiring talk.
I hope.
Before anyone asks any question, because I would like to ask you about this Rieffel product, because there might be no time to ask this later. Is this a kind of a warped product? Why did you choose this Rieffel product?
Yes.
It's a warped
yes,
product.
This is exactly. It's a warped product. It's a warped product. So actually, there are many ways to choose this. Wait, let me just scroll to that Rieffel product. Actually, von Neumann already knew it as usual, right? There is the Weil quantization, which takes you from classical functions to functions defined, on a quantum phase space. And von Neumann figured out basically that if you take the function, and instead of the e to the ipx, you insert the Heisenberg-Weil operator, you will get a deformed product. Okay, because this is what the star product is. It is also a product that is invariant under translations, or not invariant, covariant under translation. So it respects the isometry group, so to speak. And this can be applied to, so you can express all of quantum mechanics using this product and classical phase space functions. So basically, this is, and also what we figured out then in Minkowski, in non-commutative quantum field theory, Minkowski spacetime, is that you can express the non-commutativity by this product as well. But this is exactly a kind of warping. The only difference between a warping and this is this theta. But this theta is basically a symplectic structure. Okay, this is a symplectic structure basically. And also the Rieffel product, what I should say is in first order in theta, this corresponds to the Poisson bracket. And this is also an idea of Dirac. So in a sense, what is quantum mechanics? Quantum mechanics is basically replacing the Poisson bracket between two functions with a commutator. Now, and Dirac already guessed sort of the first order of that, and this is a product that does this to higher orders, and this is then related to the Kontsevich deformation formula and all this very nice stuff that people were awarded Fields medals for. So field medals for, yes.
I loved this work in a sensible manner, but you explained it very, very nicely why you chose this specific product, the Rieffel product. We have two questions from Fabio and from Nikos. And unfortunately, I didn't see who raised the hands first. Should they go alphabetically?
Let's go. Fabio should go first.
Okay. Fabio. Fabio, I think you should
have to unmute me. Yes. Okay. I'm Fabio Scardigli. I have a couple of questions. The first is a kind of curiosity, historical curiosity. You mentioned at the very beginning of your talk that even Riemann was somehow aware of the fact that physical points perhaps are not, so to say, reachable or observable. And
Right.
I would like to know what are your historical sources about these? Because I was thinking that the first person having such kind of idea was had been for perhaps Mattei Bronstein in 1935. But if you say it's Riemann, that's very interesting.
No,
So
it's way earlier. As far as I recall, he wrote it in a letter to someone, but I can't send you the exact quote. I just know where to find it, but I can send it to you exactly. The thing I think what was his idea is that the curvature, that if the curvature goes like 1 over x, then obviously if x gets smaller, this thing blows up. So he thought there should be a generalization to his geometry on short length scales. So I think that was the origin of the thought, but I can send you the exact quote.
he had some intuition or numbers about the size in which it should be.
No, he didn't. It was. I don't think he because I mean it was the 1895, I think, or something of the sorts. So I don't think he really had a number in mind. He just knew that at short length scales, this will have to be somehow his geometry, which was basically his PhD work, would have to be modified in some sorts.
Okay, I have also a second question about. I mean, you are building the mathematical framework, if I haven't well understood, to actually compute effects in non-commutative quantum field theory, like Hawking effect or Roux effect or whatever. But I would like to ask if you already have some correct, for example, for the temperature, the Hawking temperature of a black hole. Do you already have some correction to the standard formula of Hawking?
Yes, we already have. Yeah, that's a very good question, and it amazes me that you see this coming somehow. Yes, it is actually exactly so. By calculating this entropy, this should appear in hopefully in 1 or 2 weeks on the archive at least. We calculated the entropy. So there is this whole Bekenstein entropy. Or entropy bound that now recently, I think 2008, Cassini has made this a little bit more rigorous in the language of quantum field theory, and from that you can actually obtain you have the black hole entropy formula, which is some constant times the mass squared for a stationary black hole, right? And Bekenstein asked himself the question, in a sense, what happens if I throw some little mass in, right? And from that, he came up with the Bekenstein bound. Cassini was able to connect this Bekenstein bound or calculate this Bekenstein bound quantum field theoretically, although that was very difficult because none of those objects were well defined. But he achieved that in some sense. And so the Bekenstein bound gives you basically, or emerges from the black hole formula. What I did was to calculate this Bekenstein bound with non-commutative quantum field theory, and we obtained corrections to the black hole formula. And basically the corrections, depending on the deformation, of course. So if you deform only the sphere of the black hole, basically what you get are corrections to the gravitational constant.
Oh, okay.
So it goes like 1 plus something and so on, and otherwise you get actually a whole correction to the black hole formula, which is somehow a power series in the mass.
You mean the black hole, the temperature black hole, the formula of the
well, not the temp. No, what I'm referring to is the black hole entropy. So
okay.
The black hole entropy.
First you get
yes, but this should translate.
first you get a
Yeah,
correction to the Bekenstein formula, so to say,
Right.
to the area formula, right?
Exactly.
And then from there,
Exactly.
you can get the temperature. Yeah. Okay.
Correct.
Now I
Correct.
understand.
Correct. This
Oh.
is these are current these are current works that we're doing. But this is exactly sort of also one of the questions that I asked myself, in a sense, because if you think of non-commutative space-time, and usually we think of it by temperature equal to 0. But what happens if I sort of, light a fire under this? What happens with the non-commutativity? This was my question. So actually it should add, more non-commutative effects, or maybe it becomes less. We're working on this. This should emerge out. But this is exactly what I'm going for, because every theory that calls itself a viable candidate for quantum gravity comes up with corrections to the Hawking formula. So this is also what at least I want to achieve as well.
Yeah. In fact, that's why I'm curious, because when your paper will come on the archive, will arrive on the archive, surely I will read it, since I would like to see if these corrections that you find are similar, or what kind of relation they have with the correction we find with the generalized uncertainty principle. And so I'm curious to compare the two approaches.
What are okay. This is definitely so. Okay, but you didn't do it quantum field theoretically, right? So or did you?
Yeah. I mean, with the GUP, you can do for the Unruh effect. We did the full quantum field theoretic calculations. We haven't yet done for the Hawking effect. We did that for the Unruh effect for using deformed commutators, deformed in the sense of GUP, of the generalized uncertainty principle. We haven't yet done for Hawking effect, but I expect that the results are similar, since there is the equivalence principle, right? So you can essentially translate Unruh formula to the Hawking formula just via the equivalence principle, practically.
Right. I will definitely look into this. I mean, in a sense, what I didn't really dive into is I have also a generalized uncertainty principle. So instead of x and x being I theta constant, you have a theta that depends on x. But and the dependence is basically given exactly by this Jacobian. So if x1 is equal to x2, you have a theta of x, so to speak. I mean, I should have written this also down.
Your coordinates, let's say xi, xj, they have a commutator which depends on this theta function, like or not?
Correct. So the commutator x nu is equal to I theta mu nu of x, where theta mu nu of x is basically this function for x1 equal to x2.
Okay.
Exactly. So, but I don't choose that from the beginning. This is something that, so to speak, comes out from the embedding. And this makes sense if you think of it, because, I mean, if you look at flat Minkowski space, the theta doesn't depend on x, because in Minkowski space, not a lot of things depend on x. There's no curvature, the metric is x independent, and so on. But if you go to curved spacetimes, the theta has to also change with the coordinate transformation, right?
Yeah.
In a sense, so it has also to have an x dependence. This is so probably for a specific choice of embedding functions, I can even choose this such that I have. I mean, they are already generalized uncertainty principle, but I mean, I can also make specific choices here.
I see.
Depending on the embedding function.
Yes.
No, but this is a very interesting comment. I will definitely look this up and keep you informed.
Okay, thanks. Well, okay, no, let me. I have another question, but let's keep. I mean, there is a
Nikos. Please feel free to ask, because Nikos has a connection problem. Please feel free to ask. If
So
you have
okay,
I don't see other hands.
No, about the Bekenstein bound. That so you found a so to say a non-commutative correction to the standard, to the derivation of Cassini of the Bekenstein bound, right? If
correct. Correct.
Oh, okay.
Correct. Actually, what I found out is that so okay, the way they calculate, Cassini calculates the Bekenstein bound is by the formula of the relative entropy, right? So somehow he connects this relative entropy. So you know there's an entropy and there's a relative entropy, and the relative entropy is basically it's a measure of ignorance in a sense, because so let's say you have a coin, right? And it's 50-50 tail, head or tail. And if someone gives you a weighted coin that will, of course, skew this 50-50 probability, the relative entropy basically gives you the number of what is the difference of what you think will happen and what actually happens. Okay, this is what the relative entropy basically is. And Cassini could connect this relative entropy to the Bekenstein bound. He won even a prize for that, the New Physics Horizon Prize, I think. And it was a great insight, actually. And now, okay, and the relative entropy, to calculate this, the people from algebraic quantum field theory have been doing this have the tools for that since quite some time, which is basically taking the modular data, what they call the modular data. So every von Neumann algebra has this modular data, which is given by an operator by the so-called Tomita-Takesaki modular operator. Using that, you can calculate the relative entropy. And this is in the flat free Minkowski space, this is a 3-liner actually. And what I did was to insert non-commutative fields instead of just usual scalar fields in there. And then I obtained, so to speak, corrections. And what happened in the first order is that I recognized that it's not even a real correction. It's basically just the Bekenstein bound if theta is equal to the Planck length square.
Okay.
So
yes,
actually,
yes.
Yeah, which is what we always assume. But I mean, this is. So yeah, so what I'm, as I see, my whole so to speak modest philosophy here is, let me examine the heart and so to speak the real organs of this theory. Does it give us something sensible or not? And it turns out for the relative entropy, it actually tells you, yes, theta has to be Planck length square, which is equal to the gravitational constant if you set h bar and c to 1. Okay, and then you also get higher order corrections. Okay, and these higher order corrections give, if you would reverse engineer them from the Bekenstein bound to the black hole Hawking entropy, you get actually additional corrections. And it's very good that you tell me about your work, because actually I was searching for people who did this non-commutatively, because all I could find is actually works from string theory, where they come up with a sort of a new Hawking entropy formula.
Look at the GUP, not string.
Okay, very good.
Straight GUP. Actually,
that's why I just I don't look at string theory. I just know they exist.
Okay.
Say yes, but I will. I will definitely look at the GUP. Yes.
Some correction. I'm interested in this Bekenstein bound stuff because with some colleagues about 1 year ago, or maybe no, 2 years ago, we did we derived the bound directly using just it's a derivation not so rigorous obviously as the Cassini derivation and so on, but then interesting thing is that you can connect the bound, the Bekenstein bound, directly with the Heisenberg principle, essentially, and using just a standard thermodynamics. It's a thermodynamical argument. And then, if you modify the Heisenberg principle, you go from the standard Heisenberg principle to the generalized uncertainty relations. Then, of course, you get also a modification of the Bekenstein bound, and some correction to the Bekenstein bound. That's why I was asking.
You have this. You have this already calculated. So this is already a result.
Yeah. It's a paper.
Could you please send it to me? That would be really great.
Sure, absolutely. Yeah. I will send you. You. It's a paper of a couple of years ago. Yes, published on the physics. Oh
wow, that is great news. Okay, that is really great. Yes, okay. I would love to see that.
I send you the paper. Yes.
Perfect.
Okay, thank you very much for your
for the nice discussion. Is there any other question from anyone else? I think people will have to teach at 2 o'clock. I'm sure, Albert, that people would have a lot of questions.
Yeah, don't worry.
But the problem is that at 2 o'clock we have teaching, and we really.
All right.
Yes, we would like to thank you a lot for the great talk and for the opportunity to know more about your research, and hopefully we're already involved in a project with Kuwait University. Hopefully we will have you with Marcus soon in Kuwait too. So
right. Nice, I would love to come and see.
Definitely. Greetings to Germany and see you soon.
Thank you. See you soon, my friend. Take care.